We're starting section 5.5, and this is the fundamental theorem of calculus part 2, and we discussed the cumulative area function and the fundamental theorem of calculus again. So the first part was that we connected the area to the antiderivative. Now we learned about this cumulative area function, and we connect that with the function itself by derivative, basically. So I clear you question 1. True or false? If f prime of x equal to g prime of x, then f of x is equal to g of x. And you pause, and then the answer is, let me see, let me give you an example. What if f of x is x squared plus 2 and g of x equal to x squared minus 1? F prime of x is going to be 2x, g prime of x is going to be 2x, but f and g are not equal to each other. So this one is false. I click at question 2. Suppose integral from 2 to 7 of f of x dx is equal to 6 pi. What is the value of integral from 2 to 7 of f of t dt? Let's pause and come back. So all this discussion that we had was that this dx or dt or whatever that is just telling you that what is the variable that counts in here. And over here, we're learning that t is the variable that counts in finding the antiderivative. And that's all. So there's no difference between these two. And the answer, again, is going to be 6 pi. The cumulative area function. Let f be a function and let a be a number. The cumulative area function a sub f of x is going to be integral from that number a to x, where x could be anywhere in the domain of f of t dt. See, we're using f of t dt, and f of t dt is different from t is different from x. And basically t is a dummy value variable inside, and all we wanted to do is to make a difference between that t and the x that is going to be the actual variable after integration. So this cumulative area function that we just mentioned, a sub f of x equal to integral from a to x f of t dt, is the net area under the curve f on the interval a and x. Note that this area depends on x. Example, let f of t be t and a be 0, then a sub f of x is equal to integral from 0 to x t dt, and that's the basically x squared divided by 2. And so wherever the x is, you will have notes in here that the height is going to be x, the width is going to be x also. X times x divided by 2 is the area underneath, and so that's the it matches what we are expecting, basically, that and so on the notation, again, t inside is the basically the dummy variable that has no meaning outside the integral. When you integrate, you replace t with either a or when you integrate, imagine when you're integrating, you're replacing t either with x or a, and so in either case it will go away. T is going to go away. So cumulative area function, let f be a function and let a be a number. The cumulative area function a sub f of x is equal to integral from a to x of f of t dt is the net area under the curve f on the interval a and x. And so so look at this. If I'm computing AF at 0, here's the AF at 0, plugging in 0. Plug in 0 for x, and you get integral from 0 to 0 of f of t dt. We know integral from one bound to itself is going to be always 0. Now let's increase it a little bit and find the integral from 0 to 2. That would be this area from 0 to 2 underneath the curve. And then increase it a little bit. It would be the area from 0 to 4, then 0 to 6. Do you see that I'm plugging in 6 in a sub f of x, and I get 0 to 6, and then more. And now I'm subtracting the area underneath. So the a sub f is decreasing, 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 and then starts increasing again, increasing, increasing, and then if we continue further, we're gonna hit the where f of x is 0 again, and it starts decreasing again. Well, that gives me some idea why we were, let's go back, while we were in where f of x is positive, the function was increasing. As soon as the f of x became negative, the function started decreasing. And then again, when it became positive, the function became increasing. Oh, this gives me an idea that f may be the derivative of the a sub f. And because when f is positive, a sub f is increasing, f is negative, a sub f is decreasing. And so basically what fundamental theorem does for us is that, before getting to fundamental theorem, let's go over iClicker question 3. Below is the graph of a function f, and let us know what a sub f of x is doing. That is a sub f of x, integral from 0 to x of f of t dt, for x between 0 and 2, and tell us if it's increasing, decreasing, or and the concavity, about the concavity. So pause the video. Okay, after the pause, let's discuss this. So what we discussed so far is that as I go between 0 and 2, the area function just increases, right? It just gets bigger and bigger. And then and we saw it in the previous little animation. And then so area function is increasing for sure. And then how about the concavity? How's the concavity changing? It's increasing, but it's increasing with a slower rate. That is the basically it's the derivative of derivative is negative, and therefore the concavity is concave down. So increasing and concave down. So now let's discuss the fundamental theorem of calculus part 2. So if the graph of f of x is above x-axis, then the area function increases while it's above x-axis. If it's below x-axis, it's decreasing. If it's if a graph of f of x has 0, then we have a local extremum. If graph of f of x is increasing, it's the function, the area function is concave up, because we not only it's just the rate is going to be more and more, and I mean, if it's positive, it's going to be more and more. If it's negative, and the rate decrease, the rate of becoming negative decreases, that sort of things. And if it's decreasing, then concave down. And we saw an example in the iClicker, and the animation is a very good animation to go back and look at it and see why it's happening. And so the fundamental theorem of calculus 2 is going to confirm our suspicion. Suppose f is continuous on the interval a and b, then for all x in a and b, the derivative of the cumulative area function, a sub f of x, is going to be the derivative of the definition of the a sub f of x, which is from a to x of f of t dt, and it's going to be equal to f of x. So this is the fun part of it. Derivative of that integral is going to be equal to f of x itself. See, what we knew that was like this had to do with an antiderivative, but we didn't know how we take the derivative of a definite integral like that, and so now it gives us that basic knowledge of how it works. Now let's see what's the idea behind fundamental theorem calculus 2 calculus part 2. So what is the idea behind a fundamental theorem of calculus 2? We're saying that the derivative of the cumulative area function is equal to f of x itself. And so let's try to imagine this is a sub f of x, right? That the area from, and you see from a to x. And then let's try to take the derivative of this. How do we take derivatives? The limit definition of the derivative. So I have to compute a sub f of x plus delta x minus a sub f of x divided by delta x and take the limit of it. And then see what function I get out of that. So now this is, if you see there is x plus delta x marked on the x-axis, and now the total area in blue is a sub f of x plus delta x. A sub f of x is cut down with that dashed line. Now, so if I take the difference of the two, I end up with the area between x and x plus delta x. So the difference between a sub f of x plus delta x minus a sub f of x is that. And then look at this. This is really close to f of x times delta x. And then as it gets smaller and smaller, it gets even closer and closer to that. So the pink area, as the delta x gets smaller and smaller, it gets closer and closer to just delta x times f of x. And so basically, if I'm computing what this is saying is that the limit of the difference between a sub f of x plus delta x minus a sub f of x is going to be equal to f of x times delta x. It's going to be f of x times delta x. So I can find the quotient, and that would be just delta x's are going to simplify from top and bottom, and I will get an f of x. And therefore, the derivative of a sub f of x is going to be equal to f of x. So that's sort of an idea of how this theorem, and so we didn't go through every technicality, but we gave you an idea of how this theorem actually works. So a complete proof would contain all the technicalities and this idea behind it.